Hello, bacho, and welcome. So today, from our ray optics chapter, we're going to tackle a concept that, well, it sounds a little complicated, doesn't it? Total internal reflection. But I promise you, it's actually pure magic. Seriously. Don't you worry about the name. By the end of this session, you'll know exactly why diamonds sparkle so much and even how the internet gets to your phone. And yes, every single thing we discuss will be 100% exam ready. So chalo, shuru karte hain.
Okay, so to understand this properly, let's start with a beautiful little mystery. What do you think is a diamond's biggest secret? It's not about the price. No, it's something way more brilliant. I mean, have you ever looked at a diamond and just been completely mesmerized by that sparkle? Right? ऐसा लगता है ना, as if someone has switched on a tiny light bulb inside it. How does that even work? How can light, get trapped inside a small see-through stone? Well, the answer to that, Bacho, is the hero of our story today, total internal reflection. Okay, but before we can understand how to trap light, we first need to remember how light bends. It's all connected. So let's do a very quick revision of the basic rules of refraction. Super simple, I promise. So just remember there are two very simple rules here. Case 1, when light goes from a rarer medium, say air, into a denser medium, like water, it bends towards the normal, okay? But and this is the one you really need to focus on for today. When light goes the other way, from a denser medium to a rarer one, from water back into air, it bends away from the normal. Always. Our entire topic, everything, depends on this second rule.
So please, isko ekdam clear kar lo in your minds. For total internal reflection to even have a chance of happening, light absolutely must travel from a denser medium to a rarer medium. That's our condition number 1. It's non-negotiable, okay?
All right then, now for the main event. Let's see, step by step, how a light ray actually gets trapped. I want you to imagine we're underwater, okay? And we're shining a torch upwards, towards the surface of the water. Okay, Bacho, I want you to really focus on this slide. This is the whole story right here. So, step 1, we've aimed our torch at a small angle of incidence, I. See that? The light ray goes out of the water and it bends away from the normal, just like we said. Simple. Step 2, now we increase that angle I a little bit, and look, the refracted ray, it bends even more. It's trying harder to get away from that normal line. Now step 3 is where things get really interesting. We keep increasing the angle until we hit a very special, a magical angle. We call this the critical angle, IC. And at this exact angle, the light ray bends so much that it just skims along the surface of the water. The angle of refraction, R, becomes a perfect 90 degrees. So what happens next? What if we make our angle I just a tiny bit bigger than this critical angle? Well, that's the magic in step 4. The light, it just can't get out anymore. Refraction is impossible. So where does it go? It's forced to reflect, 100% of it, right back into the water. And this, my dear students, is total internal reflection. See? The light is completely trapped.
So this critical angle, what exactly is it? Let's get the official word-for-word exam-safe NCERT definition. It says, the critical angle is the angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degrees. Please isko note kar lo bacho. This definition is a 1-mark question, I can almost guarantee it. And since this is physics, of course there's a formula. The main formula is sine of the critical angle, sine IC, equals N21. Now, N21 just means the refractive index of medium 2 with respect to medium 1. But listen, don't worry about that complexity. 99% of the time in your exams, the rarer medium will be air, and we know its refractive index is basically 1. So the formula becomes beautifully simple. Sine IC equals 1 over N. Here, N is just the refractive index of the denser medium. This simple formula is going to solve so many numericals for you.
Okay. Fantastic. So let's just boil all of that down into 2 simple golden rules. These are the 2 things you absolutely must remember for your exams. These are the 2 golden rules of TIR. Without them, TIR is impossible. So rule number 1, light must be traveling from a denser medium to a rarer medium. And rule number 2, the angle of incidence, I, must be greater than the critical angle, IC. When both of these conditions are met, only then will you see total internal reflection. That's it. Simple. All right, now that you know the rules, let's talk about how examiners love to use these very rules to set traps for you.
I call them silent killers because, they can make you lose marks so quietly. But we're going to make sure that doesn't happen to you. So think about this question carefully. A ray of light, it's traveling from air into water. My question is, can this ray undergo total internal reflection?
The answer is a big, fat no. Absolutely not. Never. And why? Because light is going from a rarer medium, which is air, to a denser one, water. Our very first golden rule is broken right at the start. So TIR is simply impossible. Please don't fall for this trap in the exam.
Okay, here's trap number 2. We see the word reflection, right? And immediately our mind thinks of a mirror. But is the reflection that happens in TIR the same as, the reflection you see in your bathroom mirror every morning? No. Actually, it's much, much better. In total internal reflection, literally 100% of the light energy is reflected back. There is zero, I repeat, zero, loss of intensity. Think about it. Even the most expensive, best mirrors in the world will absorb or transmit a tiny bit of light. But TIR is perfect reflection. You see? So this isn't just some concept from a textbook. TIR is happening all around us, both in nature and in some really amazing technology. Let's look at a couple of examples.
So on the left, you see these prisms. They're used in things like binoculars and periscopes, and they use TIR to bend light perfectly by 90 or 180 degrees. They don't need any mirrors that can get old and tarnished. And on the right, well, that's an optical fiber. This is the backbone of our modern internet. A signal, which is just light, carries all our data and bounces millions and millions of times inside this super thin wire. It can travel for kilometers without losing any information. Now that is the power of 100% reflection. Okay, so now let's finally solve our diamond mystery. Look at this table from the NCRT book. For water, you see the critical angle is about 49 degrees. For crown glass, it's around 41. But just look at diamond. It's only 24.4 degrees. That critical angle is so small, it's almost like a perfect trap. Once light gets inside a diamond, it's incredibly difficult for it to hit a surface at an angle less than 24.4 degrees to escape. So what does it do? It just keeps bouncing inside again and again and again, undergoing TIR until it finally finds a way out. And that is the real secret behind its brilliant sparkle. So let's just quickly revise the most crucial points to remember. Point 1, TIR only happens when light goes from a denser to a rarer medium. Point 2, the angle of incidence I has to be greater than the critical angle IC. Point 3, right at the critical angle, the angle of refraction is exactly 90 degrees. Point 4, TIR is a perfect 100% reflection with no loss of light. And finally, point 5, it's the amazing principle that makes diamonds sparkle and powers our internet through optical fibers. So there you have it, but show total internal reflection. It's a really simple idea, isn't it? But it lets us trap and guide light with perfect efficiency. It gives us this incredible control over light itself. So I'm going to leave you with a question to think about. Now that we know how to guide light so perfectly, what amazing new technologies can you imagine for the future? Think about it. I'll see you in the next explainer. Bye-bye.